All right, good afternoon, everyone. Let's get started. Today, we are going to jump into a new chapter. It'll be pretty exciting. Let's first review where we are so far. And we completed the first section of EfficientML.ai, where we talk about different model compression and efficient inference techniques. All right, good afternoon, everyone. Let's get started. YouTube streaming. Okay. So we started with pruning, quantization, neural architecture search, which can reduce the number of parameters and reduce the precision for each parameter. And then we talk about neural architecture search. So rather than compressing existing models, how do we design a new model that is compact, small to begin with, followed by knowledge distillation to use a teacher model, train a student model, followed by MCUNet for a microcontroller, edge AI deployment, and also tiny engine. Now we are going to start a new chapter to talk about applications, application-specific optimizations. So those are general purpose optimizations you can apply to diverse neural network architectures. And now we are going to dive deeper into a few applications, including transformers and large language models. We're going to spend 2 lectures on it, since this is a very hot topic, generating a lot of attention recently. Vision transformers, not just CNNs, but also using transformers to solve vision problems, GANs, videos, and point cloud, how to exploit sparsity to exploit these applications, and also diffusion models for generative AI. Okay. So in this lecture, we are going to start with the first section about transformer and also the large language model. So large language model is having lots of amazing applications recently. For example, this is the ChatGPT. We can ask ChatGPT to make a syllabus for our course, TinyML and efficient deep learning computing. And let's see what is the given, what does it produce. Efficient neural network architectures, quantization, pruning, actually exactly what we cover, the sequence exchange, edge AI hardware, NPUs, frameworks, tools, TF-Lite, which actually makes a lot of sense. Actually, can do translation between different languages, and also the GitHub Copilot can help write the code. And the recently pretty amazing part is GPT-4 also included the vision language model. Okay, can not only process the text, but also the vision inputs. For example, we ask it, how long is the edge? What is the angle here? And it's going to say the value is here's 4, here's 8, here's 8. Therefore, we can get a C is 16 plus 64 and have square root of that. And also the angle here will be tangent theta equal to 4 divided by 8. Therefore, you can calculate theta here. Okay, very exciting. Here is a demo for the recent ChatGPT-4, where you can feed it with a visual input picture, and then ask it to lower the back seat. Actually, you can do continuous interaction, not just one image, but continuous interaction with multiple images, and do the conversation using the image as part of the input conversation. Also feed it with a menu. It's pretty complicated text in the image. So it's going to do recognize the text in the menu and match it with the toolbox. Okay, solve the problem. So let's see how is that happening, and what is the basics and foundations of such large language model. we're going to start with transformer basics, which is the building block of this amazing piece of work. And also design variants. What are the new designs, followed by large language model, and also vision language model with many advanced topics. So let's start with transformer basics. So there are two categories of natural language processing tasks. One is generative tasks, and one is discriminative tasks. For example, given an input sentence as a visual treat, the film is almost perfect. And we want to classify the sentiment, for example, of this sentence is either positive or negative. The second category is generative tasks, given the first couple of words in the sentence and predict the next word in the sentence. Before the transformer era, people use recurrent neural nets and also LSTMs to model the language. So it has the input layer, the hidden layer, and also the output layer. If we unroll this RNN in time, so this T1, T2, T3, T4, each time step you have input, you have output, you have a hidden state. And here the current hidden state depends on not only the current input, but also the previous hidden state. Okay, so it has a dependency. You concatenate the previous hidden state with the current input, pass it through an activation function, or in LCM can do more complicated operation here, and then do the output, and also contribute this to the next timestamp hidden state. So the problem here is there's dependency across the tokens, limiting the scalability. Another way is using convolution, which we are familiar with. So we have a window, and we can run convolution to have a fixed window size. But here, the limitation is that although you can have multiple layers, you still have limited context or the receptive field, right? So that has limited context information and resulting to inverse the modeling capability. Because you can only see a little window of the text. So different from computer vision, where you have very good locality in natural language. What I'm saying right now might relate it to a long time ago, what I said a long time ago. So such locality does not necessarily appear in natural language. So convolution may not always be a good primitive. Like we mentioned, there are two tasks. One is the discriminative task, the other is the generative task. So using RNN or LSTM, we can use bidirectional RNN for discriminative task, since bidirectional means you can see not only the current word, but also the future, the word in the future. Right? So it is not done offline, therefore you can have bidirectional. And for generative tasks, when generating a new word, you can only see the previous word, but you cannot see the future word. Therefore, you can only have one direction of the hidden state, right? So here, the hidden state only depends on the current input and also the previous hidden state. Well, here, one hidden state not only depends on the previous hidden state, but also the next hidden state. And here, the problem of RNN and LSTM is that if you have a long sentence in the middle, the word here, okay, if you want to get the information of chef, which was actually quite a while ago, the information of chef has gone through many layers, which is proportional to the sequence length. So potentially, it takes an order of magnitude of the sequence length to model the interaction between two tokens. So image has such kind of locality, but language may not have the locality. And another limitation of RNN or CM is the limited training parallelism. It has a dependency. Dependency kills the parallelization opportunity. It takes n steps to get to state n, making it hard to parallelize. And the numbers here means the number of steps before a state can be computed. It's propagating in the diagonal way. 0 steps, 1 steps, 2 steps, 3 steps. To solve those limitations, they build a transformer. Okay, so this is the basic architecture of transformer published in 2017, and we are going to cover different components, starting with tokenizer, how to map into tokens into embeddings, and the transformer block including the multi-head attention, fully connected layer, layer norm, residual connection, positional encoding, and also the final prediction with the linear head. And we'll start with the tokenizer. So how do we convert a word into a token that the computers can understand, which is the very first step in a transformer. So actually, what's the relationship between the word and the token? So this is a result of a tokenizer. Each color is a different token. You can see large generative models. Generative actually has been chopped into 2 tokens. Gener is 1 token, relative is another token, right? So the number of words is actually less than the number of tokens. They're roughly in the similar scale, like 1 to 5, 1 to 6. One word can be chopped into several tokens. And a single word, comma, can be a token as well. So you can roughly think a word is a token, but a token might be a smaller portion of a word. And then we want to map the token into embeddings. The naive way is to use one-hot encoding, right? Use 1000 to represent the 001, 000 to represent good, and 0001, 00 to represent movie, right? So you can represent each word as a vector that has many values, the number of value equal to the number of words. And each word has only 1 entry, that is 1. What's the problem using one-hot encoding? Right, exactly. If you have a vocabulary size pretty big, the vectors can get super long. They contain all zeros except 1 value. This is very redundant. So a natural way is to use a vector to represent, to embed each word. Okay, so to map the word index into continuous word embedding. In this case, we have 3 dimensions in the word embedding. In the reality, we may have hundreds or even thousands of dimensions for the word embedding. So here, the good movie, each one of them is mapped into a vector. There are several ways to map word into a vector, like word toolback, globe. Those are some of the early pioneer work. And nowadays, we can also train the word embedding end-to-end with a language model. So in the future, just think of each word as a vector. Each word is a vector. Okay, now comes the fun part, the multi-head attention. Okay, so we are going to cover the building blocks of the transformer block, including multi-head attention, FFM, layer norm, and also residuals. So what is a multi-head attention? So now we have a word embedding, which is a vector, maybe 4K dimension. And here we project that 4K word embedding into query, key, and value, 3 separate vectors. Okay, so here we have the word embedding, we projected as 3 matrices, QKV, turning the number of tokens by the given dimension into number of tokens by given dimension, but 3 separate vectors called QKV. So this query key value design is analogous to what? Like a retrieval system. You can take like YouTube search as an example. You have many movies. You want to type a prompt in the search bar. Okay? The query is like the text prompt, the input into the search bar of YouTube. And the key would be the titles or descriptions of a movie. And you try to see which title or description is closest to your query. And then the value would be the corresponding videos, could be a pretty large video file. And the key could be representing this value. Okay, so you multiply the query with the key to get the similarity and have a weighted average for the values. So what we do here is multiply the query, the key, to get the inner product. Make sure we want to normalize it by square root of d, so that for different hidden dimensions, it can be normalized. So this QK transpose divided by d. So after that, we want to pass it through a softmax function to get the attention weights. And what is the dimension for that? Since we have nd times dn, the resulting attention matrix is n by n. You can think of it as the weight to have the weighted sum of these values. Okay, weighted sum of the values, and the weight is calculated by QK transpose. Here we pass it through softmax. Why do we need softmax?
We want attention to sum to 1.
Yes, we want the attention to sum up to 1 when we are doing the weighted average for the weighted sum for the values. Okay, so we pass it through softmax, make it sum to 1. This is interesting. We're going to cover the attention sink phenomenon in the next lecture to see the problem that softmax brings. Okay, so the attention computation is pretty heavy. It's O(n) squared, since you have n number of tokens. It can be quite long. Like in an academic paper, the number of tokens could be like 6K. It's pretty long. You can multiply the attention weights with the value, multiply the similarity here with the value here to get the output, which is the final step. Multiply the probability matrix with the V matrix to get the final output. So this is the self-attention. I saw many companies interview question is how to write a self-attention layer in PyTorch in 10 minutes. So pretty important. So let's see, what is the attention map? This is a machine translation task. This is French, this is English, this is the attention map. We can see usually they have the diagonal pattern, since usually the word maps sequence to sequence. But here we have some reverse relationship. These 3 words versus those 3 words, English versus French, they have different habits. One is begin to end, one is end to end. They have the reverse sequence. So the attention mechanism finds the correspondence between the words. Correspondence between the words. If one head is not enough, question here.
So when researchers are coming up with this architecture, I guess it just luck, or what brought them to think, hey, this is going to be like a very key value thing they label, kind of feels like after the fact. How do they come up with these? Some of them seem really intuitive, like recurrent neural nets where you're using information before. This feels a little bit more out there in terms of just you multiply these 3 matrices together, and it's going to learn this kind of query key relationship.
Yeah, so I think 2 reasons. One reason is make it easy to parallelize rather than everything depend on the previous token. We want to be able to independently calculate the feature for each token. So that since here the QKD projection doesn't depend on the previous matrix, so we can do them in parallel. And the second reason, like we put the example over there, the query key value, those are widely used in the retrieval system, so people may borrow some idea from there. Okay, so we want to increase the number of attention maps. So rather than like a single attention map, can we have multiple attention maps to capture more detailed semantics? Okay, so here we introduce multiple head. So each head will produce 1 attention map. And here we can have 8 heads to produce 8 different attention maps. Here's a visualization of different heads. It's hard to explain why they have like this kind of pattern for each head, but it's learned end to end to capture the relationship between one language and another language. When implementation-wise, we just concat multiple has together at the output and pass it through a projection matrix. Okay, pass it through a projection matrix WO. And here we are chopping the input dimension like 4K into, for example, you can have multiple has. Each has can have a smaller portion of the has. Like you have 32 has. Each head has 128 dimensions. So the total dimension is still 4K, but you can have multiple sub dimension in each head, and you do the transformation independently, so that you can produce multiple attention maps rather than just one attention map. Like in this case, we have 8 attention maps to capture more details in the relationships. And then we introduce this attention masking mechanism. Remember, we have 2 tasks. One is discriminate task, the other is generative task. In the generative task, the token can only see the previous token. It cannot see the earlier token, the future token. Right? So here we want to have this mask to make sure that one token can only attend to the token before it. Okay? So here token number 4 only attend to token 0 to 4, doesn't attend to future tokens. Rather than, like, if we don't apply any attention mask, each token can see both the previous token and also the future token. Here, attention 4 can not only see the token 4 can not only see token 0 to 4, but also all the way can see through all the tokens. So this can be helpful for discriminative tasks. So this is the MHA, multi-head attention. The next component is the feed-forward network. Although it's just 2 FC layers, but there are so many intricate relationships here. So why do we need a fully connected layer here? So what does the self-attention learn? It learns the relationship between the tokens. Okay, but also we want to also learn those element-wise, token-wise, element-wise nonlinearities, and apply those nonlinearities to each hidden dimension. Therefore, we added this feed-forward network to help with the feature modeling for each hidden dimension. The vanilla implementation is actually quite simple, just 2-layer, multi-layer perception. We introduced it earlier with a much larger hidden state size. So we call it inverted bottleneck. And you have 4, we have D here. This is the number of hidden dimension that can range from 712K. Like in the popular 7 billion parameter model, we have 4K dimension in the hidden state, which is the hidden dimension here. In a 175 billion parameter model, like GPT-3, we have 12K here. And then we projected by the first FFN to 4D, and then pass it through an activation function. And then have another FFN to project it back to D dimension. So basically, very simple 2-layer, multi-layer perception. But we are going to see with several design variants using different architecture later. Okay, so the next component is the layer norm and also the residual connection highlighted here. We have covered multi-head attention, we have covered feed-forward, now it's the added norm. What we have learned so far, we have learned batch normalization. Okay, scenes across the batch dimension, like we have images, and this is the sequence length. Sequence length in CNN is basically the H and W, the size of the number of pixels. And you have the feature dimension, which is actually the channel dimension. So different channel, you average, you calculate the mean for the entire XY, and then you get one value, which is the bias, and also scaling factor for each channel. Okay, you have n channels, you have n such numbers. But in language models, we want to do layer normalization. Okay, what they say is nothing to do with the batch dimension, just a single batch, okay, across a feature dimension. What is the feature dimension? Here, a 7 billion parameter model, the feature dimension is 4K. Okay, across this 4K dimension, we want to normalize it. You have different tokens. We want to make sure for each token, the center is 0, the mean is 0, and the variance is 1. Okay, for each token, we want to make each token to be, you have many tokens, right? For each token across the feature dimension, we want it to be centered around 0, and the variance of 1. So we use the division here to normalize the, to do layer normalization, and followed by a learnable affine transformation of a learnable alpha, a gamma and beta here, followed by the layer normalization. The gamma and beta here is actually quite helpful. We can, this is very cheap, it's linear, right? So it's open rather than only square. Therefore, we can play a lot of tricks on the gamma and beta. For example, you can do fine tuning by tuning only the gamma and beta, especially helpful for combining LoRa with non-context. And also we can merge a lot of the quantization scaling factors into gamma and beta. Like we're going to learn in the smooth quant, the AWQ, in the next lecture, we are going to merge those scaling factors into gamma and beta in the layer norm layer. Okay, so the initial transformer, question here.
What's the intuition behind the epsilon term?
Epsilon term to prevent it divided by 0.
Oh,
yeah. Prevent divided by 0. The initial transformer is using this kind of post normalization, which is saying you have the MHA multi-head attention first, and then layer norm. FSM first, and then layer norm. But recently people find this pre-norm is actually having better accuracy. To the layer norm first, then MHA, which makes sense because we want to normalize each token, make them have a mean of 0, variance of 1, and then calculate the attention matrix. Layer norm first, and then FFN. So if you see the term pre-norm, post-norm versus pre-norm, now you understand what that means. Do the normalization first, later, or do the normalization first. And doing the normalization first, pre-norm is more popular due to better training stability. All right, now we talk about an interesting part, which is positional encoding. So far, we covered this multi-head attention, but does the sequence, does the position in the attention mechanism matter so far? It doesn't matter. We treat it as a set. The location, we don't have the location information yet. No matter where you are, they are symmetric. But that doesn't quite fit our demand, right? Rather than the set encoding, we want to have a sequence encoding to have the position information. Like a word close to each other versus a word, two words far away from each other, the meaning is different. So we want to solve this problem where attention and FFM do not differentiate the order of the input tokens, which is unlike convolutions. So the solution here is to add the positional encoding into the hidden dimension or word embedding. How do we do that? So this is the first one, positional encoding, using a unique encoding for each word's position in a sentence. Okay, so here we have two dimensions. One is the token index. In this example, we have 50 tokens in a sentence. Here is the feature dimension, okay, like 4K in Llama 7B, but here we have 128 feature dimension. And we want to distinguish token. This is token 0, token 10, token 20, token 50. We want to apply a different position encoding to different tokens and also even for each token across different features, we want to apply a different unique positional encoding. And here we use this function, okay? So sine WKT versus cosine WKT to encode the positional encoding, which is added to the raw word embedding. Like what we discussed before, the raw word embedding, we can add it with this positional information. But let's do some ablation study here. What if the T or the K gets larger? Why here it's moving pretty fast, but here it's moving very slowly across this dimension, almost doesn't change across this token dimension. And see if K is pretty large, the denominator is pretty large, okay? And then W becomes smaller. The frequency gets smaller. So that's why here you can see the frequency gets pretty small. Well, here the frequency is pretty high. It's changing a lot. So this way we can differentiate these two dimensions.
What is the intuition behind using sine and cosine?
They're periodic. So if you have a very, very long sequence, it can handle infinite inputs. And you can use different frequency to differentiate, to have to prevent it from like 2 pi. After 2 pi, you get the same value, right? But using 2 dimensions, you can differentiate that.
Any research about not just adding them, but like having sort of a weighted average, that's fine too. Right now, you're saying the position matters equally as much as the like meaning of the word.
Yes, now they are treated equally, right? You have word embedding, you have a positional embedding, add them up together. And then we can see some advanced techniques to replace this idea. So this is the original paper using the simple idea, and we're going to talk about design variants in the second section of this lecture. All right, now we put them together. They use this transformer, and this is result, showing that compared with this non-transformer result, the blue for the accuracy for machine translation is pretty high, while the training cost is 2 or 3 orders of magnitude lower than conventional methods. So transformers surpass all previously published models and ensembles at a fraction of the training cost. All right, so let's take a short break before we jump into the design variants. All right, welcome back. Let's continue our discussion about transformer design variants. So most of the initial transformer paper has been very widely used by the community, while some of the design has changed. So people proposed various alternative designs, including encoder-decoder model, and the variants including the encoder-only model like BERT, or decoder-only model like GPT. And also, rather than just absolute positional encoding, people find encoding in relative position matters. So we're going to talk about those relative positional encoding. And also the KV cache optimization, especially when the sequence gets pretty long, you have to store a lot of values in the KV cache. We're going to talk about what is a KV cache, and then how do we optimize the KV cache to make it smaller, including multi-hub attention, MHA, multi-query attention, MQA, and also group query attention, GQA. This is like group convolution, depth-wise convolution versus normal convolution. Finally, rather than the conventional FFN, we're going to introduce this gated linear units. So let's start this journey, starting from encoder-decoder, encoder-only, decoder-only models. Okay. So the encoder-decoder model has two parts, the encoder and also a decoder. This is the T5 model. And actually the original transformer used for machine translation is also a encoder-decoder architecture. Like in translation, translated English to German. This is good. This is the contents in the encoder. The result in German is the decoder's value. Similarly, we can do this acceptability task, like call a sentence. The chorus is jumping well. So this is not acceptable. This is grammarly is correct, but semantically is not correct. So the answer should be not acceptable. And this is checking the semantic similarity. So the encoder here, sentence 1, the rhino grazed on the grass. Sentence 2 is the rhino is grazing on the field. They're pretty similar. So ranging from 0 to 5, this has a score of 3.8 in the decoder, showing that it's quite similar. Our summarization, this is in the encoder. State authorities dispatched emergency crews Tuesday to survey the damage after an onslaught of severe weather in the Mississippi. And the summarized version is in the decoder, and 6 people hospitalized after a storm in the county. The encoder-decoder method is actually feeding the prompt into the encoder. This is the prompt. And the decoder basically generates you the answer. Like if you do the translation, and this is the source language, okay, you feed it into the encoder block. So here we have 3 layers. This is the token dimension, and then this is the result. We feed it into the decoder, okay, and generate one by one the target language token by token. So the prompt is fed to the encoder, and the decoder generates the answer. That's the encoder-decoder model. Another popular way is using the encoder-only model. The most popular one is BERT, bidirectional encoder representations from transformers. Okay, so it's an encoder-only language model. It's trained using one of the 2 objectives. One is the masked language model. The other is next sentence prediction. So what is the masked language model? So we are going to mask like 15% or some percentage of the input tokens at random and train the model to predict those masked words. Here, the movie is very fast, and we want to predict this is boring. Okay? So we mask it away using a special token called mask token, and we feed these tokens into the transformer, including position embedding. Okay, together with the token embedding, they're added up together, including this special token, this mask token. Okay, and it passes through this transformer encoder and get the prediction. Okay, and we supervise it by injecting classification loss right here. So what is the attention mask here? Since this is an encoder, each token can see both the previous one and the later one. Okay? So the attention mask should be the full attention. Each word can see all the words, not only the previous word, but also the future words. So the attention mask is on the top right corner. It's a full matrix. The second task, which is less often used these days, is the next sentence prediction. So given 2 sentences, whether sentence B is the next sentence of sentence A, it's a bit deprecated these days. So using this way, we can pre-train a language model to predict those masked words, and we can use this pre-trained model to fine-tune it to different downstream tasks. The next category is a decoder-only model. So compared with the encoder-only, decoder-only model, you can see the attention mask has only, each word can only attend to the previous words. That's why the attention mask is only the half of the previous one. A typical model is the GPT model, standing for Generative Pre-trained Transformer. Okay, so what is it generating? It's given the previous words and generate the next word. So that's why it's called generative. And it's a decoder-only language model. Okay, so here we are given the sentence: a robot must obey the orders given it. and then we want to predict the next word. So here we input the current word, which is 8. It attend to all the previous tokens, but not the future tokens, only the previous tokens. And we can see it happily attend to a robot. 8 actually attend to a robot, which makes sense. It just refers to the robot. Okay, and it passes through several layers of mass attention and feed-forward network, and then predict what is the next token. And also we can use 2 ways. We can either fine-tune the pre-trained model to downstream task, or we can having a larger model to have zero-shot or few-shot manner, which doesn't require fine-tuning if the model is large enough. We are going to cover several examples later. Okay, so basically just next word prediction. The next item we are going to cover is the absolute positional encoding versus relative positional encoding. Some of you already hinted this. Why do we need absolute encoding to add it to the word embedding? Do we have alternatives? The answer is yes. So compared with absolute positional encoding, okay, which will fuse those positional information into the input embeddings, including both Q, K, and V. And the information is then propagated through the entire transformer. The relative positional encoding actually providing the relative distance and injected into the attention score, into the n by n attention map, by either adding a bias to the attention map or modifying only the query and the key. So the key, the V is not modified. The V is not modified. So it's different from the first case. So the advantage is that it can generalize to sequence length that have not seen during training. We train short and test long. Usually we have this long sequence requirement, like summarize a whole paper, which can have like 6K tokens. What if the model is trained on only 4K tokens? It hasn't seen if the positional encoding, it is absolute, it's from 1 to 4K, it's absolute. How do we extend it to 6K or 8K? So relative positional encoding has the advantage here to train short, test long, but it's not working naive. If you do it naively, it requires some tricks to make it actually work. We are going to cover those tricks. So that is the advantage of relative encoding. You can train short and test long and generalize to a longer sequence than what we have seen in the training time, since it encodes the relative position, which makes sense. If a sentence, the two relationship between the sentence, no matter which location in the text this sentence is, the meaning might be similar. So let's see 2 examples of relative positional encoding. One is this alibi encoding, the other is this rope embedding. Let's see first this alibi encoding. So the idea is to change positional encoding only related to the relative distance, but not the absolute index. Right? So here is the attention map. We have Q1, 2, 3, 4, 5, and K, 1, 2, 3, 4, 5. So this is the original attention map, And this is the relative positional encoding. If Q and K have the same index, the relative index is 0 because they have the same index. But this one is Q2 and K1, differ by 1. Okay, so that's why this diagonal part is all 1, including here. This is 1, 2, 3, Q3 and K1 and K2. Right? This is Q3 and K2 differ by 1. So everything in the diagonal part is the same. Like here, this is Q5 and K1. Therefore, this is 4. Okay, so only the relative distance matters. The absolute position doesn't matter. That's why no matter what is absolute this location, as long as the relative location is different by 2, this value is 2. And we manually set a scaling factor and we'll add these up together. Okay. So what's the difference with absolute encoding? Previously, we are adding the word embedding with the positional encoding, the raw word embedding for QKV. Now what we are adding, we're adding the attention map with the positional encoding. So this is just adding this offset to the attention matrix defined in the relative distance instead of adding it to the input token embeddings in QKV. Another approach is to use this rotary positional embedding. This actually is the key part of the Llama tool. We're going to see that in the homework, very popular these days. It's a very popular implementation for the positional embedding, like we used in Llama. And what it does is actually rotating the embeddings in the 2D space. Okay, so we split. So this is the word embedding. And we split the embedding of D into D divided by 2. So we group every 2 elements together. Okay, so each pair, like a pair here, is considered as a 2D coordinate. Why do we need a 2D coordinate? So that we can rotate in the 2D space. And we apply our rotation according to the position M. First token, second token, third token, sixth token. Okay. Enhanced transformer with rotary position embedding. We have 6 tokens here. We divide the hidden dimension of each token, group them by 2. Every 2 elements are together, forming a 2D coordinate x1, x2, x1, x2. And we use this M, which is position, to multiply by a constant theta, okay, to rotate by m theta. M theta. So the larger the M, more you are going to rotate. And how do we define the theta here? It's actually 10,000, so power of -2 I minus 1 divided by d. And why do we need like 10,000 here? We need a big number to distinguish more tokens. Since if you do the rotation, you rotate by 2 pi, you go back to the original value. You cannot distinguish them anymore. So every time we have to move like a little bit so that we can accommodate more longer tokens rather than like pass through 2 pi. Okay, that's why here we need a pretty big number. It cannot be infinitely big, otherwise we are too small, cannot distinguish them. Basically, when you are doing the dot product of two vectors, what is happening there? So if you do this is doing the transformation, you rotate it by m epsilon, and when you are doing the dot product of 2 vectors, both you pass it through this rope transformation, you can see we are multiplying the norm and also subtracting the angle. Okay, since the phase angle of the inner product of 2 complex vectors, okay, is basically the phase difference between these complex vectors. M minus n. So this is the relative difference. No matter how big n is, the difference matters, not the absolute value. Okay, so that's why here this is the relative positional encoding.
So where is the position for embedding this case? So we're still just adding it to the regular embedding, or we're doing something else now that we have next. Now that we have
so this is only applying to the Q and K, not to V. Therefore, it's impacting the attention matrix. Since the dot product, rather than directly dot product between Q and K, okay, now we do the transformation of Q, do the transformation of K, and then do the dot product. And the value will be related to the relative distance of Q and K. And V is not changed. That may answer your question.
You're not adding this number to the dot product. You're doing the touch mechanism, and then this is a new layer.
Yes, exactly. is that we are not, it's a bit more complicated than just simply adding it, or we're changing the equation to calculate the dot product. Rather than dot product between Q and K, we're doing dot product between the transform the Q and transform the K. So I really like the color here. So you can see the result. This is every two values, they have the same color, but it's also mingled with this red color. Red means its location. Okay? And here is mingled with this green color. This green is this location. And what is the implementation here? So like we mentioned, rather than directly doing QK dot product, we do the transform the Q and transform the K. What is the transformation? This is the transformation matrix. Okay. We have the first one, we can see every two elements are grouped together. So every two elements is grouped together, share the same rotation angle. Okay. Since two elements, X and Y, can rotate in 2D space. And here, D divided by 2, since originally we have D dimensions, now since we're grouping every two of them together, that's why we have D divided by 2. All right, so that's the transformation. And let's see, how do we extend it to longer context, which is one of the key motivation. We want to train short and test long, right? Train short, test long. Say previously we have seen only 2K tokens, right? During training time, we have seen only 2K tokens. But we want to attempt to generalize that to 4K tokens. What is the naive approach? You just extend it from 2K to 4K and use the same data, but M is from 0 to 4K. Actually, that doesn't work. You cannot directly fix the same data and just increase the number of sequence knots here, right? So what does theta mean? Theta means the rotation angle. Since you have a longer context, you cannot rotate the same angle. But if you double the number of sequence, you should rotate only half. Okay, so the correct solution here is actually theta equal to theta divided by 2. Okay, so you are actually squeezing to the same region rather than rotate by 2 circles, still rotate the same amount, squeeze more points, 4K points into the same range. So that's the way to train short and test long. All right, so that's positional encoding. Now let's talk about another important concept, which is KV cache optimizations. Again, it's related to long context when you are keep chatting with a chatbot, or you want to summarize a very long document. We are going to introduce multi-head attention similar to normal convolution, multi-query attention similar to depth-wise convolution, and grouped query attention, analogy to the grouped convolution. So what is the KV cache? So we are talking about the GPT style, which is very popular these days, decoding only. Okay, we want to store the keys and values of all the previous tokens, since each new token is going to see all the previous tokens. And rather than recomputing it every time for each new token, since they are the same, we can store those key values for the previous tokens when we have a new token. Since they're the same, we don't have to recompute each time. We call it KV cache. So this is the example. So far, we have 3 tokens, I, love, Sweden. Okay? So we are currently at time T2. And this X2 is going to append to all the previous tokens. There's 2 tokens. Okay, so it's going to append to this is the query, this is the key, this is the value. This is the Q, the query of the new token Q2. It's going to multiply with the K0 to calculate the similarity. Remember the YouTube example, this is search bar, this is the video's description, right? We want to see the similarity before we do a weighted average, weighted sum of the V of the value. Okay, so the Q2 and K0 is 0.3, Q2 and K1 is 0.1, and Q2 and K2 is 0.6. So we need to calculate, we need to store the key for all previous tokens, and also similar for the V. Okay, they stay the same no matter if it's Q2 or Q3. And you can imagine as a sentence input sequence gets longer and longer, the amount of value we have to store will grow linearly. Okay, ultimate time will grow really long. Let's see another example. What happens if there's no KV cache? This is the video. So in this video, there are 4 steps. Then we have the QK transpose, and multiply with V, and finally as the attention. So without KV cache, for every new token, for example, here we have to calculate this 2 by 2 matrix. And here we're 4 by 4. We have to recalculate everything. But actually, the beginning portion is actually shared across across token 1, 2, 3, and 4. So actually, we are wasting time calculating the previous regions. And we use that QK transpose normalized version to multiply with V. So what if we have the KV cache? If we have the KV cache, same 4 tokens, the previous calculated K and V can be cached rather than recomputed. So the purple part for the K and purple part for the V remains the same across different tokens. Therefore, you don't have to recompute the QKT for each token. Like previously, you already calculated Q1, K1. Now you don't have to calculate it when you are at Q4, Q3. Similar here, you already calculate Q2 and K2. Now you don't have to calculate it in the future step. But the overhead is that you have to store this purple part in the memory, and that grows linearly as the sequence length gets longer. And how long can it be? So we give you some real-world examples. How do we calculate the size of the KV cache? The intuition is that it will grow linearly with the sequence length. That's indeed the case. What is the other factors? First of all, the mini batch size. 1 user, 2 users, 3 users, certainly that grows. A number of layers. Each layer has its different K and V, so each layer has its KV cache. And each head, remember we have multi-head attention, so each head will have its KV cache. And the KV cache is proportional to the hidden dimension, right? Hidden dimension is large. Each word requires a 128 size vector, so that's the embedding size. KV cache size is proportional to the embedding size. And also it's proportional to like K and V, right? You have K, you have V, that's why you have 2 parts. You have to multiply by 2. And here is the sequence length. You want to summarize a long document versus a short document. So the KV cache size is proportional to the document size, and also 2 bytes for IP16 representation. So for every token, every batch, you need half a megabyte for Llama 7B. Similarly, we can calculate Llama 2 or 13B. Okay, for 13B, the number of layers increased from 32 to 40. And the number of heads increased from 32 to 40. The hidden dimension, each head remains the same for different Llama models, 128. Length, KV, and 2 bytes per 2 bytes. So this 800 kilobytes per token per batch. What if we use 7B, Llama 2 7B, using MHA, multi-head attention? KV cache double the layer from 40 to 80. Number of heads also increased to 64. There is 2.5 megabytes per token per batch. And let's see what that means. 2 megabytes per batch per token. If batch size is 1, number of sequences is 512, you need 1.25 gigabyte to store the KV cache. What if you want to summarize a paper? I could give you an iClear paper. You want to summarize it, you want to review it, give it some questions. It's roughly 4 to 6K tokens. And 4K tokens require 10 gigabytes of memory. The GPU has 80 gigabytes of memory. What if we serve 16 people, like everyone in our classroom, we submit a job to GPT-4, submit a paper, wanted to summarize it for us. 16 people, one paper, 4K tokens, that require 160 gigabytes of memory. And that require 2 A100 GPUs just to hold those the KV cache, not even the activations, not even the weights, just the KV cache. What if everyone in MIT want to do that service? Can you imagine that? That's pretty big. 2 A100 GPUs, each one is 20K US dollars. And that's 40K, just serve everyone here in our classroom. That's can get quite expensive. So we urgently need to reduce the size of the KV cache. This is even assuming this is Llama 2 7B. GPT-3 is 175B, and it's even larger. GPT-4 is even larger. So what do we do with it? Oh, by the way, this is showing the linear growth of the KV cache. Okay, so here is the batch size of 1, 16, 32, and this is KV cache size. This is the model size. Okay, so we can even surpass the model size. This is a calculation, batch size, number of layers, number of paths, hidden dimension, number of tokens, and KV. So people propose several techniques to reduce the size of the KV cache by reducing the number of KV paths. So multi-head attention is very important to capture the relationship between the query and key, right? Between the query and key. We still maintain the same number of heads for the query. We may have different queries, but we want to reduce the number of keys, reduce the number of values. Just like the YouTube example, we want to reduce the number of movies. Okay. So there are two cases. This is the original case. The other two cases are multi-query attention and grouped query attention. So multi-query attention is saying we can average all the values and keys into one value and also one key. So in this way, we can reduce the number of KV has to only 1 in this case. So you have you reduce from n has for KV to only 1 has for KV. For the attention, you still have n attention max, since query you still maintain n number of queries, n has of queries. But certainly that's like batch-wise convolution, it sacrifices the model capacity. So another way is to do grouped query attention, which is in the middle between multi-query versus multi-head attention. So grouped query attention is saying several, you group several key and value together and reducing the number of heads. So here we have 8 heads. Now we group every 2 together and we have only 2 heads in this example. So typically we're reducing by 8 times is a typical number. For example, Llama 7B, we have 32 heads. So now we can have 32 divided by 8. We can have only 4 heads. So this is showing the reduction. So previously, this is the size of the KV cache using MHA, multi-head attention. And this is using the grouped query attention. The size is reduced by 8. Okay, since the number of head H here reduced from 64 to 8 in this example. This is using the multi-query attention, the purple here. is 64 times smaller, because previously we had 64 heads. Now everything is merged into only one head. So the reduction of the KV cache is pretty significant. But what about the accuracy? So this is showing the performance of the multi-query attention, group query attention, compared with the baseline, which is the multi-head attention. So you can see on the Llama 2 30B with 150B tokens, the GQA, the group query attention, actually matches the accuracy of multi-head attention under the large model sizes, like 30B model. But a multi-query attention, the accuracy, you can see some degradation about the accuracy, which makes sense, because in this case, you are losing the most information. Well, if you select the right amount of group number, like here is 8, it's maintain the accuracy for even using group query attention. And as a result, this is also used in the largest Llama 2 model, the Llama 2 7B model. All right, the last one is from FFN to gated linear unit. So previously, when we are talking about FFN, we assume it's an inverted bottleneck due to faulty ReLU or GADU activation function. But improving over this FFN, people propose is gated linear units, GLU, okay, which actually contains 3 matrix multiplications. So the first one, second one, and third one. Okay, and here we are using the element-wise multiplication as a gate. Okay. So first, D to 8 divided by 3, D is also inverted, but the size is smaller than 4, since we want to maintain the total computing the same. And then we pass it through a switch activation function, and we're going to see that in the next slide. Pass it through this switch activation function, and then have element-wise multiplication, and finally project it back from back to D. And this is showing the complexity using different architectures. For example, using GLU, gated linear unit, versus not using that. Using the switch GLU, switch activation function with gated linear unit is performing pretty well. And here using the GE-GLU is also performing quite well. But recently this switch activation function plus gated linear unit is getting very popular. So people chose that one, which gave a very good accuracy. So the lower the better for the perplexity on the right-hand side. And this is showing the activation function for GADU and also for switch. The only difference is the parameter here. And the overall size, overall shape of the activation function is pretty similar. All right, so that concludes the second part. Now we are going to dive into popular large language models by combining the techniques we have learned so far. Actually, recent years, the number of parameters in large language model is growing super fast. And because when we have larger number of parameters, the emergent abilities appears. Only the emergent abilities only emerge with model that is large enough. Like in this task, modified arithmetic. In this task, 1 plus 1 becomes 3, 2 plus 2 becomes 5. Basically, like adding 1 to the final result. So 100 times 200 plus 200 becomes 301. It's modified arithmetic. We want to, like the large language model, to do such tasks. And we find only when the training flops is larger than like 10 to the power 22, then it can have good accuracy on this task. When the model is smaller than that, compute is smaller than that, cannot solve such problem. This is another interesting problem for word unscrambling. Like the word HTE is a scrambled version of the English word the. If you rotate the sequence, this is the word the. or if you want to scramble this HPTO, it's actually photos. We want to have large language model to do such tasks, but it's only possible when the training flops is greater than like 10 to the power of 22. So LLM exhibit such emergent abilities that are only available with large enough model size. And GPT-3 scaling up transformers to be few-shot learners, which is introducing a new concept called in-context learning. Okay, so what is in-context learning? Traditionally, for downstream tasks, people have to fine-tune a pre-trained model for different downstream tasks. You have 10 downstream tasks, you fine-tune 10 times. Like you want to like a pre-trained model to do machine translation. You have to give an example, train it, get a gradient, update the model, give another gradient, give another example, get a gradient, etc. To fine-tune the model. Finally, you can handle the new task. So this is traditional method. So zero shot is basically saying that we directly describe the task in our prompt. We don't train a model for different tasks. We use the same model across different tasks. And how do we specify the task? We put it in the prompt. Translate English into French, give this English word. Okay, so this is zero shot. Predicts the answer only given a natural language description of the task. No gradient ever happened. No fine-tuning actually happened. Okay, very good. We can actually add a few more examples to improve the quality. Okay, so in addition to the task description, we also see a few examples of the task. Like here we have 3 translation examples together with this task description, translate English to French. And then we feed it to a new prompt and soon will give you a good answer. So this is showing that these larger models, like 175 billion parameter model compared with this 13B or 1.3 billion parameter model, these larger models can more effectively utilize these few shot demonstrations. As you can see, the accuracy is much higher for the 175 billion parameter model. And on the right-hand side is showing that with one shot, zero shot, one shot versus few shot, the more example you gave, the higher the accuracy. When the model is large enough and the number of examples in the context is large enough, even without prompt, no task description, compared with task description, the accuracy is pretty much the same, saying that you even don't have to tell the model translate English to French, hide this part, just give 3 examples. When the new task, new word came, it can automatically predict the answer. And when you have large enough model, large enough examples, we can match the accuracy of with language, with task description versus without task description. So these are the evolvement of these GPT models from 2018 to 2023. Okay, after 5 years, increased by several orders of at least 3 orders of magnitude. This is just so amazing. This is where I started my job at MIT, and this is so amazing to see such big advancement versus the GPU memory actually haven't quite catched up. So there's a huge demand to bridge the gap between the fast increasing demand versus the supply. OPT model, which appeared last year, okay, when I was teaching last year, this model just appeared. Different sizes from 125 million to 7 billion, 60 billion, 175 billion parameter. It's open source, retrained language model from Meta. It's a decoder only model. Pre-norm, use pre-norm only except for one of them, and using the ReLU activation function in the FFN. For the 175 billion parameter model, the hidden size is 12K. 96 has vocabulary size is 50K. Time context length is 2K. It's a bit short, cannot handle a paper very well, which usually require like 4K or 6K. And the performance is relatively comparable to the GPT model for zero shot applications and also the few shot applications. There's also a Bloom model, okay, which is using the pre-norm and also the Gadu activation function. You construct the Gadu activation function using the alibi positional embedding. Remember the alibi positional embedding, just adding this relative position into the potential map. 0, -1, -2, -3. Okay. And support multilingual 59 languages in the corpus. Llama, this appeared this year, which is getting a lot of contribution to the open source community. It begins to use this 3 GLU, a switch activation function, gated layer units rather than 2 FFN layer, 3 matrix multiplications. There is a switch activation function together with an element-wise dot product using the rotary positional embedding, the rope positional embedding, which is covered in the lecture. And it's getting pretty good accuracy compared with different models. Much better performance compared with previous open source models. And the most popular one is probably the 7 billion parameter model, hidden dimension of 4K, 32 has, each head has 1.8 hidden dimensions, 32 has. And the Llama 2 is even better. It's trained on even larger amount of tokens, okay, from 1 trillion to 2 trillion tokens. And no sign of saturation yet. You can train longer, actually, the performance for this 7B, 13B, 34B, 7B, 70B, and probably even increased. And it's using the GQA, group query attention, which have been introduced for larger models like Llama 2 70B, which has 64 has, but only 8 KB has rather than 64 KB has. Also introduce the instruction tuned model so that you supervise that with the feedback so that you can handle conversation better. And here is showing comparing the performance. This is GPT-4, this is now. And this is the Falcon model. Okay, so it has pretty big hidden size. Maybe catch number of layers pretty similar. Comparable performance as Palm 2 large. A very interesting one is recently this Mistral 7B model. It's a pretty small model, but it's claimed to outperform Llama 13B and also Llama 34B. Very well trained. Hidden dimension is also 4K, 32 has. KV-CAD is 8 using GQA, group query attention. So the interesting part is not only the GQA, but also introduced this sliding window attention, okay? Sliding window attention rather than the full vanilla attention. It's using the sliding window attention. It's no longer O(n) square, sliding window size by n as the complexity. In one layer, the effective window size is pretty limited, but if you stack multiple layers together, the receptive field is going to finally, you can see all the tokens to the back. Like here, you can only see window size amount of tokens before you, but across many different tokens, different layers, you can finally see a much longer effective context length. So the dream of scaling up never stops. So the Chinchilla law is saying that as we scale up the number of parameters, the amount of training tokens, you have to also proportionally scale that, right? So they not only increase the number of parameters, but also you have to increase the amount of training data. So data engineering, data collection, data curation, very important job. Llama 2 breaks this rule using a much larger number of tokens. So 7 billion parameter model, according to Chinchilla law, require like 200 billion tokens. But Llama 2 increased by 10 times, use 2 trillion tokens to train it and give you a very good performance. And we are going to use that in the homework 4, lab 4, which is released today. Welcome to check it out. We are going to do quantization on it and also deploy it on our laptop. All right, we're over time. This is so exciting. We are going to continue to cover advanced topics in the next lecture.